Hi everyone, this is Prof. K speaking, and today we're going to talk about electrolytes. Our learning objectives for today are to define and give examples of electrolytes, to start to distinguish between the physical and chemical changes that accompany dissolution of ionic and covalent electrolytes, and to relate electrolyte strength to solute solvent attractive forces. So what is an electrolyte? An electrolyte is a substance that undergoes a chemical or physical change in water to yield ions in solution. And a non-electrolyte, or everything except this group, are substances that don't yield ions in water. So if I put sugar in water, if I put some glucose molecules in water, nothing happens besides that I have some sugar in water. So sugar is a non-electrolyte. It's not doing anything when I dissolve it. If I put something like sodium chloride in water, it falls apart to form sodium as a positive ion or a cation, if you remember last semester, and it forms chlorine as a negative ion or an anion. And so sodium chloride would be an electrolyte, whereas glucose or other things that don't ionize are going to be non-electrolytes. And once again, like with solubility in Chem 14 and when we talk about it in general, if you have a non-electrolyte, you have basically no dissolved compounds are ionizing, or exactly no dissolved ions are ionizing. Weak electrolytes might be situations where only some amount of the dissolved compounds are going to ionize. So this might be something like a weak acid that we talk about. And so weak acids don't completely fall apart to form hydronium ions and the anion of the original acid. Only some portion of them fall apart. So they could potentially be contributing to weak electrolytes. Strong electrolytes, on the other hand, are things that just fall apart completely when they hit the water. You immediately have sodium and chlorine. They immediately separate into ions, 100% of them. So they're strong electrolytes. And in particular, this shows up as how well you can use them to conduct electricity. So electrolytes a little bit implies that we want to do something with electricity. But if you have a non-electrolyte, there's nothing charged in the system that could move between negative and positive plates. So nothing happens here. There's no electricity that this system can conduct. If you have a strong electrolyte and everything is ionized, then you can apply charge to the system and it will cause these ions to move in different directions, which will generate electricity and can transmit charge, and you'll have a bright light. If you have only partial dissolution, like in the case of, or only partial ionization, as in the case of weak electrolytes, such as weak acids, then there's only some charged compounds that can help us conduct electricity. So we see less light coming out of this system powered by the electrical conductance. And so this is why it's useful, and also a way that we can measure whether or not something is a strong or weak electrolyte. And so what's happening in terms of the intermolecular forces for these systems? So if we put something in water, like sodium chloride, or in this picture, potassium chloride, the ions and the dipoles of the solvent it's being dissolved in have electrostatic attraction that allows the waters to solvate the ions and pull apart the physical block that was the solid or the material before. And so water is dissociating this ion, and it's the physical change where ions in the solid are solvated or surrounded, like we talked about in our last video, and interacting with the waters in this ion dipole attraction, and they're pulled apart and dispersed in our solution. And this dispersion in the solution, surrounded by waters as separate ions, helps us conduct electricity, because once they're all spread out, you can move them back and forth and get charge out of it. And so this is helpful, and it comes from the fact that dipoles are happy to interact with the ions here. And so you'll notice if you look at these particular waters that the parts of the water that's trying to touch the chlorine or that's having an intermolecular interaction with the chlorine is the partially positive end, and the partially negative end is staying farther away from the chlorine. The potassium, however, is interacting with the partially negative end of the water molecules, because that's the attraction of the negative and positive charge. But overall, what you get are potassiums and chlorides surrounded by waters, even if they're interacting with different parts of them. And so this helps us do that charge movement that we need to be an electrolyte. And I mentioned in the previous slide that some acids and bases are also helping us do electrolyte chemistry, because if you have a strong acid and a base, when you add that acid to water, it completely dissolves, it completely ionizes, and it forms H3O plus and chlorine. And that's a lot of ions that can then go on to interact with water in the similar way. And we call these covalent electrolytes because there's ions with covalent bonds. And so in the previous slide, I had K plus and Cl minus. There's no covalent bonds in either of these, so they're ionic electrolytes. Whereas here, we have covalent bonding within our ion. So that's why I'm using the language covalent electrolyte or ionic electrolyte. And weak acids are a good example of weak electrolytes because they're only going to generate a little bit of H3O plus and a little bit of their anionic form. And so this can help us predict whether or not a particular compound could be a strong or a weak electrolyte based on whether or not it's a strong or weak acid. And so it might be helpful to review some of those weak and strong acid chemistry as we move into this section, just because it can help us remember why something might be a strong or a weak electrolyte.